Yeah, thanks a lot for the invitation. It's, of course, a pleasure to give a talk here. And I should say that I'm extremely grateful that we are able to host this event here in Bonn. So thanks to the organizers. The title of my talk is, what is it? Holomorphic functions on sectors. But maybe these are things that I will maybe only come to a little bit later. Because really the main object that I want to study in this talk is the following, like, very basic linear algebraic kind of datum. So I will study the following data of just V, some topological vector space. And I could work over the real numbers, but because I will do some kind of eigenvalues and so on in a moment, it's better to immediately pass to the complex numbers to have all the eigenvalues defined over the base field. Let's say I have a topological C vector space. And I mean, not just that, but also I say I have an endomorphism of it, a self-map T. And for the beginning, it won't be really important, but somewhat later it will be important that it is really an automorphism. All right, so that's a very basic, very general datum. What can we kind of say about this? So, I mean, the zeros example of the situation is, of course, if V is finite dimensional. So in this case, well, T can be given by a matrix. It has an eigenvalue decomposition. So in particular, we can always write V as a sum of its generalized eigenvalues, right? So V is for lambda in C, or because we actually assumed it's invertible and a non-zero number, we have a generalized eigenspace. I was told not to write too much on the right side because it becomes invisible from the left side of the hall. The generalized eigenspace V lambda inside of V, and then V always just decomposes into the direct sum over all possible eigenvalues of the generalized eigenspaces. And so I guess this can be called a spectral decomposition of V. And so pictorially, I like to think about this as follows. So you have your C, and then you puncture it at 0. And then in this finite dimensional case, you will have just finitely many points somewhere here, lambda 1, lambda 2, lambda 3. And then using this spectral decomposition, you can somehow localize the whole representation V as a direct sum of pieces V lambda 1, V lambda 2, V lambda 3, that you can kind of think of as sitting at those points. And then the whole thing is somewhat the union of these things. Okay. So, yeah. Finitely supported. All right. And so as the next example, I want to look at maybe the case before we somehow make things topological. So let's study the situation where we just have some abstract discrete C vector space with an automorphism. With an automorphism. So what are some kind of new infinite dimensional examples one could think about? Well, whenever we pick any vector inside of V, then because we have this automorphism, we get lots of new vectors, right? We can translate it by T. So if we have any V in V, then we somehow get a sequence of vectors V squared. But it's an automorphism, so we can also go to the left and get all these vectors inside of V. And then maybe somehow the universal example in some sense is the thing which is just generated by one, and then you just freely add these things up. So for example, you could just have a direct sum over all n and z of C times some basis vector En, where T sends the basis vector En to En plus 1. And well, this doesn't really have any eigenvalues, right? If you try to find something that's an eigenvalue for this operation, then some of the scalars in front of all the n's would have to be the same, but you had a direct sum here where only finitely many are allowed to be non-zero. So this doesn't have any eigenvalue decomposition in the usual sense. But I mean, the structure that you still have, so in general, like if you just apply this idea of that whenever you have a vector, you can somehow have all these translated, and you can also sum them up. Somehow E becomes a module, actually, over a larger ring, over this polynomial ring in C adjoint T and T inverse, which is precisely basically the same thing, except the ENs I now call AN times T to the N, where almost all AN. And I mean, such modules can be roughly understood. So they're basically, there are two special kinds of such. The first are the torsion modules. So torsion means that whenever you have any vector in V, you can find some non-zero element in here which kills it. And then actually some equation algebra of this will act where you mod out by this, and then actually the finite dimensional thing will act. And then actually these things have always an eigenvalue decomposition. So then V is actually a direct sum of V lambda lambda and C star, where these are still the generalized eigenspaces. But now as V is infinite dimensional, you could very well have the case that infinitely many of these V lambdas could be non-zero. Infinitely many or even all can be non-zero. You can still think of your V as somehow being decomposed into pieces sitting at specific points, but just spread out at possibly infinitely many points. So there's something. I don't know, lots of points not talking to each other. And like if you kind of study such V vectors, such modules up to those that are torsion, then somehow up to things that are torsion, you can assume that everything acts invertibly. So you can also have the situation that all T minus lambda, where lambda is in C star, act invertibly. So you don't just have a kernel, so an eigenspace, but also they act surjectively. So then V actually becomes a module over the thing where you are also allowed to divide by all of these things. And in this case, you actually become a module over the fraction field. of this ring. and so that's some of all the structure there is. So you just get a module over the fraction field, a vector space over the fraction field. And then there's not much more you can say about the structure of this because, like, vector spaces over a field, they all have a basis, so they're just completely classified by their dimension. So basically, they're like these torsion things which you can nicely spectrally decompose. Or in this case, well, this doesn't sit at any particular point, but it somehow sits everywhere else. So, it sits over the whole space. So in algebraic geometry, we call this a generic point. Right, so when in pure algebra, we're trying to do such a spectral decompositions of modules. Still have a bit of space here, let me write it here. So in pure algebra, some of the spectral decomposition of such modules, C adjoint TT inverse modules, happens over some space that is conveniently called the spectrum of this thing, which is just C star, so it can have a spectral decomposition at those usual points, and then one generic point eta. So as a topological space, these are all closed points, and the closure of this contains all the other points. So this specializes to all the other points. So topologically, it's a very ill-behaved space where you have this one generic point which somehow sits everywhere and specializes to all the other possible points. So you don't really have a nice geometric localization of the module. Is there anything to erase? Yeah. Right. Okay, so now, from now on, I will study the case where D is really a topological space. And I mean, there are many different kinds of topological vector spaces. So let's start with maybe the most convenient class, which is a class of Banach spaces. And when we use a Banach space, it has a norm on it. And maybe as a first pass, let me also assume that T preserves the norm. So in this case, whenever I have any vector in V, I again have this picture that whenever I have my vector, I can translate it under T and under T inverse. And these have all the same norm. Because I did assume it was the automorphism was preserving the norm. And so in Banach spaces, you know that you can somehow form convergent sums. And so now you don't just have finite sums of these, but you can form certain infinite sums. Which kinds of infinite sums? Well, for all sequences, or bisequences, an, where n is in Z, which are summable, so these ANs they are complex numbers. We can form also sum of an times t to the n v, and produce a new vector inside of V. And so this actually makes V a module over a ring or even over a Banach algebra. One way to denote it is some of the space of summable sequences parameterized by the integers. So some an times t to the n, or the sum of the absolute values of these ans. Finite. And you can check that if you multiply two such sequences together, the product will still be in there. So what is the structure now? Well, Kvam actually generalized this notion of, or maybe he didn't generalize, I mean, this was before the spectra were in algebraic geometry. He defined the spectrum of such a commutative Banach ring. Which is somehow the one that you can sometimes localize over in this case. And in this case, it's just S1 inside of C star. So just the complex numbers of absolute value 1. Namely, this algebra is actually just isomorphic to the continuous functions from S1 to C. While taking such a series and then you have such a sum, you send it to this thing that takes any lambda in C star of absolute value equal to 1 to the sum of an times lambda to the n, which is well defined because of our summability condition, and by some kind of Fourier series, these are actually exactly the same. And so it turns out that in this case, one can actually analyze the structure of such a Banach module in terms of this much more geometric space S1 instead. So. So any V, as in the example I'm discussing right now, so Banach and D preserves the norm. Has a certain spectrum of V, which is a certain closed subset of the spectrum of the relevant algebra. Let me just call it Z. So what's the geometric picture now? So we had this Z star that we always have. Now our modules in some sense certainly always just supported on the S1, but depending on which module you have, it might just sit at some interval here, and then you might also have some isolated points, and I don't know, some closed subset here. And in a suitable sense, you can write V as an integral over this closed subset of pieces V lambda, where lambda ranges through Z. So that the idea is that the finite sum decomposition you had when you had just a discrete set of points can be generalized to some notion of like a direct integral over such a continuous base space of possible eigenvalues. Whenever I write this notation, what I secretly interpret this as that there is secretly a sheaf on this topological space whose stalks are these things, and then integral means take global sections. But I think this integral sign nicely captures the intuitive idea. And for example, this means that if lambda is an isolated point of Z, then you can always write V as some generalized eigenspace at lambda and something away from lambda. At lambda. Or slightly more generally, if you have a decomposition of Z into two open and closed subspaces, then you can always write V as a direct sum of a piece of V that's somewhat supported at Z1 and the sum that's supported at Z2. And actually, this norm-preserving property of this automorphism wasn't very relevant for this discussion. So more generally, if V is still assumed to be a Banach space, but T is any automorphism, not necessarily preserving the norm, any continuous automorphism. Namely, one property that Banach spaces have is that any possible automorphism kind of automatically preserves the norm up to rescaling. So some of them must exist, some radius r greater or equal to 1, so that the norm of the operator T and of its inverse, they are both at most R. So previously, someone discussed the case where R was equal to 1, but in general, there exists some bound. And so this means that if you look at the sequence of these iterates that you get here, they might grow a norm, but it's controlled. Like this might be R times as large, R squared times as large, and also these can somehow grow, but there's some control over how fast that could happen. And so this means that V still becomes a module over a slight variant of this algebra I had over there. This time you are allowed to take those sums, so multiplying by n times t to the n, where the growth condition is, or the summability condition is that if you sum the an, absolute values of the an times r to the absolute value of n, because both t times the vector and t inverse times the vector, they both become larger, so you have to write the absolute value here. This is finite. And what is this algebra really? Well, these kinds of power series, you can evaluate them at any lambda provided that the absolute value of lambda somehow satisfies these same conditions. And so this actually becomes those functions from the set of lambda in C star such that 1 over r less or equal to lambda is less or equal to r. Oops. Right, from this kind of annulus. So, right, so we have radius r and radius r inverse. And then we have this annulus here. Functions from here to the complex numbers. They certainly must be continuous. But because they have such a power series expansion and this head has non-empty interior, they must actually be holomorphic in the interior. So concretely, this has a slightly curious consequence that if you have any such function f, so for any such holomorphic function f, there's somehow a new operator f of t also acting on v. So this is called the holomorphic functional calculus. That whenever you have such a holomorphic function with some condition that's it's defined on the spectrum of your v, then you can apply to an operator. So you can define the sinus of an operator or the exponential of an operator or something like this. So it's called the holomorphic functional calculus. And I'm from like the data of just a topological vector space with an automorphism probably at first doesn't indicate that this is somehow about holomorphic functions, but some holomorphic functions appear completely automatically in the study of these things. Like if you just had a continuous function here, then you couldn't in general do it. It is some kind of coincidence of this case of the S1 that all the continuous functions can act. All right, and so then, I don't know, so the spectrum of V is then, again, some closed subset of this annulus. And then it's even a closed subset, in fact, of C star. And so same story. So V can again be written as some kind of integral of some kind of eigenspaces in the suitable sense. Right. And so, in particular, to get a statement that's completely independent of the choice of R, the algebra of holomorphic functions on the whole punctured plane will act on all such Banach V with an automorphism. Right? Because when it's defined on all C stars, and no matter what R is, it will be defined on this annulus. Okay, and so the story for Banach modules is in this way pretty well understood, but there are many interesting topological vector spaces that are not Banach. And one example I would like to point out is that you could also take something like a Laurent series in T. So these are those sums, an times t to the n, where n is equal to 0 when n is sufficiently negative. So these are some of the wrong series expansions of holomorphic functions. But there's absolutely no growth condition on the ANs when n becomes positive. And so there's no way to put some kind of norm on this because, I mean, these can be arbitrarily large, so there's no way to put any bound on this. It's still some kind of reasonably well-behaved topological vector space. I mean, it's not quite nuclear Fréchet, but it's a co-limit of nuclear Fréchets. And so certainly multiplication by T is an automorphism of this. Well, where in this picture would this sit? So if I think of this as somehow, I want to kind of also write this as some kind of integral of eigenspaces. Somehow, where would this should this be? Well, what are power series? Well, you have here, and if you just hit the power series, I mean, these are just power series expansions of functions at 0. So this is something that somehow sits very, very close to 0 and just sees some of the infinitesimal behavior of a function to all orders near 0. And so it's very, very, very localized at 0. It doesn't yet belong to our realm where T is an automorphism because I didn't yet make T invertible on here. But if I do, then somehow I take this thing and then make a very, very small punch in the middle. And so that it lives on the punctured thing. But it's visibly extremely concentrated at 0. So it's extremely close to 0. And certainly, whenever you pick any of these annuli that we studied so far, then it certainly is not at all supported on those annuli. It's like much closer to 0 than any of these annuli. So not contained. In any annulus. And so it's quite unclear how you could ever try to achieve any kind of spectral decomposition that should somehow appear on the C star itself, because the C star itself is somehow the union of all these annuli, and it's not on any of these annuli. But if we slightly change our perspective, and I mean, I kind of already did when I was talking about these annuli so much. Let me use really radial coordinates on C star. And let's first just try to achieve a decomposition according to radius, so where we somehow group together everything that lives on a circle. Then we might think that there's somehow still some kind of boundary circle near 0, and this indeed happens. So for any so now I need to make some niceness assumptions about my topological vector space, and some kind of standard mild assumption is complete locally convex. Topological vector C vector space V, and actually this time I could just use an endomorphism for this statement I'm doing right now. There is a radial decomposition that you can decompose this into an integral, and sometimes from 0 to infinity, of something supported at a given radius. So VR, you should think of as being supported at the locus where the absolute value is equal to R. Where important is that these pieces at 0 and the infinity may well be non-zero. So for Banach spaces, somehow they would be concentrated on a compact subset of this interval, closed interval from 0 to infinity. But for a general topological vector space, like for the C power series T or C long series T, there might be contributions that somehow are localized away near 0 and infinity. And this contribution at 0 can, of course, appear if T is just an endomorphism, because then you might have just C with a 0 endomorphism. But even if T is an automorphism, this can appear. So for example, this C, if V is this, then this is also just the things. There's just a 0 piece. So for this thing, the radial decomposition doesn't do anything because it's all concentrated at 0. I should note that there's something slightly funny happening. So I said at the beginning of my talk that when V is just an abstract C vector space, then we can really only, then we're in the realm of pure algebra, and we can only do a decomposition according to this algebraic geometry notion of spectrum, which had these closed points, but then just one extremely blurry generic point. Whereas now I'm giving you a much finer decomposition, and the hypothesis applied to any discrete C vector space. And abstract or discrete or whatever you want to call it. I mean, without any real topology, C vector space. The thing is that the constituent pieces are not abstract vector space anymore. They carry an interesting topology. So in this case, so somehow to get this finite decomposition, we have to leave the realm of pure algebra and have go to some world of topological modules, in this case. Constituent pieces have an interesting topology. Basically, if you just apply this to the free C adjoint TT inverse module, then those constituent pieces will be basically algebras of holomorphic functions on annuli. I have to be, because this doesn't really contain any open subset, you have to be slightly careful about what I mean by this, but that's the idea. Note that a general principle of this formalism of direct integrals of vector spaces is that the full thing can be smaller than an individual constituent piece, but that's just a general phenomenon. But so in this way, you're kind of localizing, globally, algebra into locally complex analysis. Okay. But very near 0, you're somehow not doing much, because this doesn't apply to Right. And so I said I want to use these radial coordinates, and I come at some in a radius direction. I told you what to do. But what about the angle direction? And so I mean, there's a map from C star you can project to S1. Just they contract or it just remembers the direction, like r times e to the I theta maps to e to the I theta if you want. And so the preimage of such a thing are now in our picture. We just take a line here and a line here, and then have some part like this. So such a thing is called a sector. And so when you have these Banach modules, then I mean you could somehow localize them. I mean you could really localize them on the full closed subset here, and so particularly you can group this according to radius, but you could also group this according to these sectors. So Banach things can definitely be localized in this way. The question is, when you have something like C Laurent series T that's very, very close to 0, then can you extend also this kind of sector, this kind of localization, even very, very close to 0? So, question. Can all such V with an automorphism? And now it's manifestly important that it's an automorphism, because if I just had the 0 endomorphism, there's no way I could localize this on a circle. So this is why I started with an automorphism in the beginning of my talk. Can all such things be somehow written as some integral over S1 of some V theta? And an example to keep in mind would be like this algebra of Laurent series in T, which is very, very close to 0. And so somehow, can you split that up as the global sections of a sheaf on S1? And the usual algebraic geometry intuition, which I kind of said already fails, would tell you that no way, I mean, this is a field, this is a spectrum, this should just be a point, there's no way you could split this over a circle. But if you're hoping for a positive answer, then you can also ask, if so, then which kinds of functions can act on V if the support of V in the S1 direction, so somehow as a kind of sector support, is contained in some closed subset Z inside of S1. So we somehow previously said that if the support is contained in some annulus, and some of the holomorphic functions on that annulus know how to act on V. If we, in some sense, one can show that having such a spectral decomposition here is somehow the same thing as finding algebras that know how to act whenever this V has support in some prescribed sector. So, and this finally leads us to the title of my talk, namely these holomorphic functions on sectors. I mean, so the naive idea that you would is that on such a sector, you would somewhat like to take some kind of holomorphic functions on the sector that maybe, I don't know, maybe are kind of small, remain kind of bounded, maybe extend to continuous functions on the whole sector or something like this. Because that's more or less what you had on these annuli. And so, but you have to be, yeah, I mean, and this is also basically what works. So, right, so. Except you kind of always want that T inverse can also act. And T inverse is somehow a function that becomes large near 0. So you kind of have to take that into account. But you can study just the following algebras. So if Z inside of C is such a, or inside of C star is such a sector, meaning somehow that the argument of your variable is constrained to some interval. You can look at functions from the sector to the complex numbers, which are holomorphic in the interior. And have at most polynomial growth towards the origin and infinity. Because I'm a locally near 0, if it has polynomial growth and then you multiply by sufficiently large power of t, then you can make it even decay. So this is a natural class of functions to consider. And studying such algebras on sectors is something that's a very traditional topic in complex geometry. So many many holomorphic F from, like, I don't know, C star to C have asymptotic behavior at, say, 0 that depends on the sector. So so the standard example of this is f of x is the exponential of 1 over x. Right, so 1 over x is well defined and the exponential is well defined. So we have 0 here, and then I want to draw this imaginary axis because what happens when x is a positive real number, then 1 over x, when x is a small positive number, then 1 over x is a large positive number, and so the exponential of this is very large. So when you approach in this direction, then you have exponential blowup. And if you think a little bit about this, the real condition that you needed for this was not maybe that x is positive, but that the real part is positive. So also when you approach this from such directions, you will always have an exponential blowup. Whereas if x is negative, x is like small but negative, then the 1 over x is large and negative. And then the exponential of this is very, very small. So if you go on the negative axis, then this has exponential decay. And again, the real condition was that the real part of x had to be negative for this. When you do some more complicated versions of the same examples, for example, 1 over x squared, then the sectors become slightly more complicated. Namely now, you somehow have to draw these lines of those. I mean, these are some of the lines where if you square them, you land on the imaginary axis. And so then you will have, in this region and this region, exponential growth. But in this region, I don't know, you have decay. And actually, on the boundary line, you actually have a totally oscillating function. Just an exponential of I times some real number. So here, if you're really at this line, then it's oscillating. I think this kind of phenomenon goes under the name of Stokes phenomenon. And it's very relevant for the study of D-modules with irregular singularities, where typical examples of solutions would be such functions. So these satisfy some simple linear differential equation. And when you study solutions to this, you somehow have to take into account these different growth conditions. And so the idea is now that you can try to form, find the correct way to decompose and general such V according to S1 by somehow declaring that, for example, this exponential 1 over x function can act on V, but only if the support is contained in this left sector. Or this function can act if the support is contained in these factors where it has exponential decay. And I guess I'm basically out of time, so let me just end by stating the theorem. It's easy. And I was very confused what actually happens to this example, but it turns out that on such a sector, with algebras on sectors, they need not have any asymptotic expansion at 0, but sometimes they do have such a Laurent series expansion that somehow you can show that to first order they have some kind of limit value, and if you subtract that, then they have like linear decay and then divide by t and get a new limit and so on. And so sometimes they can have such a Laurent series expansion. And actually all possible Laurent series expansions, even the ones with no convergence at all, can be written as Laurent series expansions of such functions on any sector that's not the full thing. And actually, if you localize this to a sector, you get the algebra of all functions on a sector modulo those which decay faster than any t to the n. And okay, but yeah, so in particular, yeah, like all such complete locally convex as before. Even the ones coming somewhere from algebra, they admit this localization. And let me just end with one remark. So in terms of, so all of this belongs to some kind of long-term project I'm developing with Dustin Clausen of condensed mathematics and analytic stacks, and some kind of general framework of extending the techniques of algebraic geometry to analytic geometry. And really, when I talk about complete locally convex vector spaces here, I have in mind liquid condensed vector spaces. But these are particular kinds, so that's OK. And what happens here is that just the usual algebraic GM over the liquid complex numbers actually has some argument map that goes to S1. And so this means that in our version of that somehow between algebraic and analytic geometry, even the algebraic GM has some kind of universal cover. where on the universal cover, the logarithm function to see. The logarithm function is locally well-defined on the algebraic GM, because the logarithm function is well-defined on sectors. I mean, it's a holomorphic function on each sector because they can choose a branch of the logarithm, and it has only logarithmic growth. In particular, it has most polynomial growth, so it is a well-defined function locally on this guy. And so, yeah, a lot of things that traditionally belong to the realm of pure complex geometry can, using, in particular, the existence of this map, be in some sense algebraized. Okay, let me end here.